welcome to day 11 of our 30-day coding challenge here from CSandMath. We're going to revisit abstraction today because I cut it a little short. I tried to put in the day we did integrating characters. And so we're going to talk about how to write functions for our three components and how that fits the concept of abstraction. We're going to bring in some more math functions or equations. And I'm going to try to make a few connections to the block-based language Scratch because I figure a lot of people have at least seen that or used it. So let's get started. Okay, so yesterday we imported, or we should say wrote, the algorithm that sweeps or paints the points across for your equation. So if you run and execute your code, it should do our three things: grid the plane, make the axes, and draw in. For this purpose right now, we just put in a parabola. Could have had anything, like remember we used the y equals x line. If I regraph this, and it draws just like a y equals x line. Now there's a lot of different equations we can do, and we'll do that here in a minute. We just want to abstract the code out first. So I'm going to undo, I'm going to redo that. So I'm actually going to start with just one of them, let's say. In order, we did the axes first. So we set the size to 200 originally to initiate. We don't have to put that in the definition. So let's say, let's write it like this. So defines the xy axis. We could say, definition, and we'll call this draw axes. How about? And for that, we actually want to take in the parameter size, right? Because if we use this size, if we call the function and we could put an argument in there that says what size we want it to be, now that value plugs in here, and it plugs in all the places. And then all we have to do is make sure we tab in all the code that fit within it. And so now if I run this, check out what happens. Notice how the axes aren't drawn? It's not going to do this because we've defined a function, but we haven't called it. Okay, so I'm going to stop that. Then this code here is going to do both the horizontal and vertical. This time I'll put the comments right in there since there's two of them. So I'll just say the definition of this one we'll call draw grid, which can also take in the parameter of size. And now I would just highlight all of that code. So it doesn't want to let me kind of roll up there. Not let you do that. If I highlight all this code, luckily I can get it all, tab it in. And usually it lets you drag further down the screen. Yeah, if you do it downward, it lets you. So again, now if I've defined all this as draw grid, if I ran this code, none of it would draw because I haven't called it, but it would still draw the equation. Okay, so I was just looking through the program, and I think this is a pretty good idea that we've covered. We could do a lot more, but I think what we've done here shows these are our three main components, and all we're doing is running those three things. Now, this is an idea called abstraction because if someone was trying to use this calculator, they wouldn't really have to know much, right? If you had somebody using it, they wouldn't really have to know how that code up there worked. Notice how it doesn't like that I got rid of size. What I thought I would do is go up and say wherever we define this size, I'd just pull that out and put that with my executable program. That way if anybody wanted to change it, they could change it easily, quickly, right in this little structure. And the only part we'd probably want, again, is the equation, because you want the person using the graphic calculator to be able to put the equation in really easily. So that part is not awesome the way we have it at the moment. But so what I could start with maybe would be better is if I go to, again, the definition of abstraction, just to help you. This is from the K-12 Computer Science Organization. They do a really nice job of making things just kind of clean and concise. But it says the process of reducing complexity by focusing on the main idea, hiding detail, irrelevant to the question that's at hand, right? And so sometimes we just want to hide things, essentially, that are really tricky for people. In terms of this product representation, it's saying a new representation of a thing. Again, hiding details irrelevant to the question at hand. This is so crucial to really grasp in decision making for programming. So for example, like if you go to Scratch, now I just searched Scratch. It's here's the address if you want it, scratch.mit.edu. But if you go here in the upper left, it'll say create. And if you click that, it'll bring you into this interface. Now, most of our lessons on our website, CSandMath, are actually written in this language because it's the easiest for people to access, especially early. So if you looked at our stuff, you're going to see that our lessons are written with Scratch. So if you wanted to explore this, it's really a great program. But they might, like if I go to this sensing menu, these, by the way, are like modules, similar to like the modules we're importing with, let's say, Turtle. If I wanted to do like sensing two colors are touching, how in the world does this block work? Or this command, I guess you'd think of it as, work? How does it sense like the distance from my mouse pointer to this cat? Well, they programmed it in and they disguised some of it. Like notice how this ask block just asks. It doesn't convert to an integer. They've hidden some things, right? And that's really important to understand. Or another easy one to grab would be in the events, I guess it is. When this sprite is clicked, is a block. That's basically, this thing's called a sprite, like an object or character. If I click this, it knows that I'm clicking it. If I had the motion, I could actually, when I click this thing, it could move, right? So this is something that they've chosen to abstract, whereas in Python, we would have to, if we wanted to do that kind of interacting, quite a bit of programming is required. This is at the essence of abstraction. To give a cleaner picture, like let's say, for example, you've used GeoGebra. We use it a ton in math classrooms. Or you could use something similar like Geometer Sketchpad. Notice there's all these tools. Well, like for example, we use this midpoint tool a lot. If I had 2 points out here, A and B, and I wanted to find the midpoint between them, right, I could just click those two endpoints and it finds the middle. Well, how in the world is it doing that? They've chosen to abstract it out. There are a couple ways, like you could make a circle. If you've done constructions before, you know that there's a way outside of this to find that midpoint. They've chosen to abstract it in a tool. And so the same type of thing here, with this way we've written these functions, if you were someone coming in to use this, you could easily play around with this code and don't have to understand all of this other stuff in it. In fact, let's go back to the TI calculator. So for example, if I downsize this, remember how we talked about this TI calculator? To use this thing, we don't even need to know what we did, how we made this grid, how you resize the grid. There's so much stuff that's programmed into here. It's just you don't have to know to use it, right? Because they wanted to eliminate that from view. But we think some of it's really crucial in thinking, and it can really help kids and give them a better experience just in general of their mathematical understanding. But if I hit graph, right, the graph shows up, and I don't actually have to know how to make it. All I have to be able to do is change the equation in here, right? And if I go back, oops, if I just clear it and I type an X in there and I go back and graph it, it just shows up for us. So we can just use it versus worried about how it works. And this is a graphical user interface. So you just intuitively know how these buttons work. In fact, your whole computer, if you think about my computer screen here, I'm on a PC. Microsoft Windows computers didn't always run off of this. I have a mouse on the screen, I have a background, and I have icons to click. It didn't always work that way, right? Sometimes text just popped up. I'm just trying to give you a good understanding that those are all systems of abstraction. You might even be wondering, well, how would you get some of those graphics in here? And if I end the video in that way, again, I'm just trying to give you some stuff today. I don't know if I did exactly what I said I was going to do. But in programming, this is called the graphical user interface, the GUI, and you have to have text. You have to have pictures coming in versus just text. And this is a little harder on Python platforms currently. But if I look, they say this is pronounced two different ways. It's called tkinter, some people call it, or some people just call it tkinter. But this is currently the recommended graphic user interface module that doesn't yet work on Trinket, although Pygame and some other things where you can pull in images work. But yeah, we can maybe talk about that on a later video. So hopefully this is helpful. I didn't cover, I think a bullet point on there. Maybe I can cover tomorrow how to get in like, let's say we want to do trigonometry, other functions. I can show you how to bring in other equations. All right, thank you guys for tuning in. Hopefully that gave you some understanding and was helpful.